Hi, I'm going to explain some part of the theory. First, we will begin by explaining some of the rules and norms established, especially by the US government, to use certain colors for the wiring. The black wire is commonly used as the hot wire, also known as phase or live. This wire carries the current from the power source to the device or load. If we have more than one phase, we can use wires in orange, yellow, brown, and less commonly red and blue, since these colors are also used for low voltage circuits, meaning positive 24 volts and digital ground are connected with these respective colors. The white or gray wire is used for the neutral conductor. This wire carries the current back from the device or load to the power source. The green wire, or in some cases green and yellow, is used for the ground conductor. This wire provides a safety ground connection to protect against electric shocks. AC single-phase motors commonly use both a centrifugal switch and a capacitor for starting and running purposes. Centrifugal switch. In single-phase induction motors, there is a need to create a rotating magnetic field to start the motor. However, since single-phase AC power alone cannot produce a rotating magnetic field, to overcome this limitation, a starting winding is used along with a centrifugal switch. During startup, the centrifugal switch is closed, allowing the starting winding to be connected in parallel with the main winding. This creates a rotating magnetic field.
Let's dive into how a single-phase induction AC motor, specifically rated for 127 volts AC, according to its motor nameplate, is electrically connected. To connect this motor, you'll follow a straightforward process. First, identify the motor's specifications on its nameplate to ensure it's indeed rated for 127 volts AC. Next, you'll need to connect it to a compatible power supply. In this case, a 127 volts AC supply is required. That is why we use the AC outlet. Now let's look at the wiring. Typically, a single-phase induction motor has two power leads. According to the motor nameplate, you'll connect one of the hot wires, often black or red, from the power supply to the first motor lead, which is made of wires T1, T3, and T5. That is blue, orange, and black. Then connect the neutral wire, usually white, from the power supply to the second motor lead, which is made of wire T2, T4, and T8. That is white, yellow, and red. And that's how a single-phase induction AC motor rated for 127 volts AC is electrically connected. The operation of start-stop buttons, normally open and normally closed contacts, involves a simple yet effective control mechanism commonly used in industrial applications. Here's how these components work together. The start button, normally open, is a typically a momentary push button switch that is normally open when not pressed. In its resting state, not pressed, the normally open contact of the start button is open, which means there is no electrical continuity to this contact. The stop button is also a momentary push button switch, but is configured as normally closed when not pressed. In its resting state, the normally closed contact of the stop button is closed, allowing the electrical continuity through this contact. An electrical interlock is a safety feature used in electrical system to prevent unsafe conditions or sequences of operations. It involves the use of interlocking devices or components that control the electrical circuit based on specific conditions or sequences. The main objective of electrical interlocks is to prevent hazardous situations or accidents by enforcing safe operational sequences. These use electrical signals or switches to control circuit operations. For instance, a relay may prevent the starting of a motor unless certain conditions are met.
For this practice, we have had a simulation, and I'm going to explain it. First, we have an electrical motor connected to the physical ground, the digital ground, and here's a signal connected to the line. And this signal from the motor is connected to a contactor. We can see it is connected to number 2, and it's normally opened. So then this contactor is connected by the number 1 to a motor word, and physically we have a motor word and a breaker, but here we only have this full component that includes the motor word and the breaker, and this one is connected to a fuse, and the fuse is connected to the line. Then that's for the power part, and for the control part we have a start button, we have a stop button, both of them connected to the to the voltage, and then we have a coil that is going to keep the information when we start this simulation, and they are connected to the negative part or to the ground. And here we have a memory that is going to help us to keep the engine working, and it's going to stop when we push the stop button. Here we can see how it works. First, we need to turn on this, and then when we push the start button, this normally open contact is gonna close, and with this coil, information is kept in this coil, and we can see that the signal is still going, and the motor is working. When we use the stop button, the signal is gonna come here, and this normally open contact is gonna turn off, and it's gonna be normally open again. So when we push the stop button, it's open again, and the memory of the coil is now off, and we can see that the motor isn't working no more. So start, it's working, it closed, and when we push stop, it's not working, and it opens, and that's it.
Now I'm going to explain how is the power phase working. First, we have here in these screw terminals, we must connect from the plug of the lab, the line, the neutron, and the ground to this lower part. Here, these ones are interconnected between them. So in all this space, we have lines. Here we have the neutron, and here we have the ground in these green ones. So as you could see in the simulation, from the line, neutron, and ground, we must connect it first to a fuse. In this case, we have this electrical interlock where the fuse is inside, and this will allow to protect the circuit in case of a short circuit if there is a small or well considerable amount of current. Then we must connect this line to the thermal relay. The thermal relay acts here as a second barrier or second phase of protection for the whole implementation. Here we must connect it to one of the inputs, and in the output of this one is connected to the protective motor. Before I start with the protective motor, I'm going to explain what happens with the voltage source, the orange one here in the middle. This one, its work or its function is to give us 24 volts in digital current output and a digital ground, a direct current, I'm sorry. So we must connect the line, the neutron, and the ground to this voltage source, and as an output, we will have the 24 volts in direct current and the digital ground, which is going to be used later on in the control part. So explaining that, then a return to the thermal relay is going to get connected to the protective motor. In their first two terminals, these ones are connected here and are joined by normally open contact, which when the whole thing energizes, it's going to close. So this is important because this little switch over here is when you implement this, you put it on a certain position, and if there's a problem, it'll open. So it'll stop the flow of current to the motor. Why could a problem happen? An overheating of the motor, probably a short circuit bigger than the interlock could handle and the thermal relay. So it will stop the current from flowing, and it'll, as its name says, it's going to protect the motor. So we have these two connected. We activate the implementation by this switch. This switch is going to allow the current to flow to all the other phases of the implementation explained in the simulation. But well, it's going to let it flow here, and it is going to close here. But what is important is this part of the contactor. In the contactor, we have these 3 pairs or 6 terminals, which are for the alternating current part, and these 2 pairs or 4 terminals for the control one. That's why you could see this blue cable of the digital ground. So we are not going to focus on these 4 terminals, and we'll see these 3. These ones, this is number 1 and number 2, the same as in the simulation, and these are going to energize or close the normally open contact, which is between them, when the switch is activated in the control part. So in the power part or power phase, we only have to connect these 2, and as you can see, the output is connected to these other screw terminals, which are connected. You can see that by the color of the wire. The black wire is connected to other black wire, which is the black wire of the motor. So here we have all that vertical line connection we had in CADESIMU in that simulation. Well, we have it implemented here with all these real components, and that would be all for the part of the power phase, in which importantly we have these third barriers of protection for the motor and the whole implementation. Obviously, we have that these are normally open contacts. This is going to energize or let the current flow. I'm sorry, and this one is the voltage source, which will use the energy from the plug, as you can see here, that is connected to the line, neutral, and ground, and will get us a digital current instead of an alternating current for the implementation. So that will be all in the part of power. Thanks.
So now I'll explain the functioning and more specifically the control part of this circuit. So first of all, we have 4 main components. We have a start button, a stop button, the coil, and the normally open switch, which these last 2 are placed in the contactor. So the way this works is that, as we can see in the video, when I press the green button, the motor starts running. And this is because the green button closes the switch, and this allows the electricity to flow all over the circuit, energizing the coil, which allows the motor to start running. Now, we have a normally open switch that when the coil is energized, it also energizes the normally open switch. And this allows an infinite loop that the coil energizes the normally open switch, and the normally open switch allows the coil to be energized. And this makes it running in an infinite loop. Now, in order to stop the motor, we have to press down the red button, which, as we can see, stops the motor. And this is because the red button is connected right behind the coil, and by pressing down it, the red button is a normally closed switch. So when I press it, it opens up, and this de-energizes the coil, and therefore it de-energizes the normally open switch, shutting down the whole system. And in order to turn it on again, we have to press the green button. And this is basically how the control works in this circuit.
practice, I learned the importance to know wiring norms to have an organized setup in any electrical system implementation, so there are no confusions when connecting the wires to the terminals. This is very important because here in Mexico, we use the American norm, and we must know it because it's the one that is implemented in all the engineering companies here in Mexico. Also, the amount of components of protection and execution needed to start a 127 volts AC motor, where the power phase and control phase may be together, but we must interpret them separately and make sure to know which component belongs to one or the two phases at once. This is very important because we must know how each component works, how it's related to our motor, and how it's the simulation implementation looking like. So if we look at this simulation, we can now know how to connect these ones and make sure to know which are the terminals of each of the components and if we must wire them to the alternating current or direct current.
In conclusion, through this project, we have not only acquired new knowledge and skills related to electrical systems, but also gained practical experience in designing simulations and implementing modern control systems. This hands-on approach has deepened on our understanding and prepared us for the future endeavors presented in our personal and professional life.
Well, now as my conclusion, I can say that through this practice, I learned about how by means of a push button panel and the design of the pertinent connections, a motor starting mechanism can be created as well as its shutdown. And the most important part that it's not mainly or specifically about the theory, it's that I gained experience about how to connect the different elements existing in the system and the precautions that we have to take when we are applying them, because it's something that sometimes we do not care about, but through this practice I learned that they have to be as important as other parts of the practice.
Personally, for me, this practice has been of such a high importance since it has involved both the theoretical and practical knowledge. We as a team have demonstrated proficiency in developing control systems that depend on power electronics. We have learned from some mistakes and also our successes, which in the future of our academic and professional lives will have such a great impact.
During this practice, I learned about the essential components used to control and protect a 127 volts AC motor in an industrial setting. The integration of a motor protection switch and control devices like start and stop buttons is crucial to ensuring safety and efficient operation of electrical equipment. The experience gained better prepares me to work safely and efficiently with AC motors and associated components in professional environments.